One of the key things we've got to do with these new functions as we learn them is obviously we need to know how to differentiate them and integrate them so we then can use them in our calculus. So let's have a look at differentiating our logs. Okay, so if we have y equals log of function x, and by log with no base there I'm meaning a natural logarithm. So if y is the natural logarithm of function x, the derivative turns out to be the derivative over the function. So whatever you're logging, that function, its derivative on the top of the fraction over the original function on the bottom of the fraction. Okay. Now, if it's any other base, it's very similar. The only difference is on the bottom of the fraction, you also multiply by the natural log of a. And that's why you don't have it in the first one, because the natural log of e would just be 1. And so it doesn't appear in the derivative if it's a natural log that we're differentiating. But any other base, then on the bottom of the fraction we'll also have the natural log of the base. Very rare we'll get questions where the base isn't natural. By the vast majority will be natural logs that we'll be looking at. So okay, so now to differentiate something like this, it becomes very easy. This one's just a linear function. So if I had to differentiate the log of 3x plus 5, well, the derivative is 3 over the original function 3x plus 5. We could do this one two ways, actually. So we've got y equals log of x cubed. So I could say the derivative is 3x squared over the function x cubed, and then x squared and x cubed simplified down to be just 3 on x. The other way we could do it is before we differentiate, we could use our log laws and bring that power to the front and say, oh, well, that's the same as 3 times log x. And then when you differentiate log x, you'll have derivative over function. Well, the derivative of x is 1 over the original function is x. And again, we get our answer 3 on x. So just a preference which way round you would go with something like that. The log of log x. So the function that we're logging is log x. So to differentiate, it would be the derivative of that function. Well, the function is log x. So to differentiate log x, it would be derivative on function. So the derivative of log x is 1 on x. That goes on the top. Over the original function, log x. So tidying that up, we get 1 over x log x. Something like this. Log of x plus 3 times x plus 2. Okay. The derivative, now on the top I've got to use a product rule, so write down the first, diff the second, plus write down the second, diff the first, over the original function, which is x plus 3, x plus 2. Tidying up the top, I get 2x plus 5 on x plus 3, x plus 2. Or, again, I could use my log laws and break that up into 2 logs. So that's the log of x plus 3 plus the log of x plus 2, which actually gives me 2 functions that are very easy to differentiate, because the derivative of x plus 3 is just 1, as is the derivative of x plus 2. And so you've got 1 on x plus 3 plus 1 on x plus 2, which is the answer. Obviously, I could use algebraic fractions and come up with the same answer. But I guess it all depends on what are you doing with the derivative. If I was finding the equation of a tangent, well, I could just as easily substitute into 1 on x plus 3 plus 1 on x plus 2. I don't actually need it to be all one fraction. If I was finding stationary points, well then, yeah, okay, I probably need it to be one fraction, because I'm going to say I'll solve that equals 0. So it really depends what sort of problem we're using the derivative for. But as I say, we can get the other one. So we get our common denominator, x plus 3, x plus 2, and sure enough we get the same answer if we were to keep going. So similar idea when you have a quotient there that we're logging. So if I use the quotient rule, square the bottom, write down the bottom, diff the top, minus write down the top, diff the bottom, over the original function, let's tidy that up. Well, the top fraction becomes minus 3 on x plus 2 squared. Then invert and multiply by the bottom fraction. The x plus 2's, we've got some cancelling, and we end up with minus 3 on x plus 2, x plus 5. That's kind of messy. A lot of places I could make mistake in the algebra there. If I was to use my log laws, then I would separate them into two logs. You've got log x plus 5 minus the log of x plus 2. Differentiate each of those. And again, depending on what we're using the derivative for, that might be good enough. But I could keep going. Algebraic fraction, get a common denominator, and we do come down to the same thing. And in fact, maybe with a division one, the second method is easier from the point of view of spots where we could make a mistake. But once again, it's just personal preference, how you would prefer to go. So here's one where the base is not a natural base, it's base 10. But as I say, it's just the same. Derivative over the function, so 6 over 6x, but we also multiply by the natural log of the base, so we get log 10 on the bottom.
Would it still work if we change the base to make it a natural log?
Yes, because if you change the base and made it a natural log, you change a base rule would say, well, that'll be the log of 6x over the log of the old base. That's why the log 10 comes on the bottom. So that's actually where that comes from. But it saves changing the base first. We just know, okay, well, I'll end up with that log of the base on the bottom. 6's in this case will cancel. So I've got 1 on x log 10. Alrighty. Couple exercises. Enjoy.